Hello everyone, I'm Farah. Welcome. Today we'll dive into SDLC and DevOps, two essential practices that shape how we design, build, and deliver modern software. Have you ever noticed that many projects fail even when the code technically works? That's because success is about more than just working code. Features break at the last minute, one small change can ruin everything, and after a while, no one even understands the code anymore. Well, the problem here is complexity. Software starts simple, but as it grows, even tiny mistakes can break the whole system down. Without a structured approach, things become unstable, unreliable, and impossible to maintain. Now, let's use this simple example. Imagine you're at a movie theater. The ticket clerk asks for your name and age. If you're old enough, you get in. If not, you're politely told no. Either way, your name and age are saved and logged in the system. Pretty straightforward, right? But what if this little system goes? Suddenly, you need to change how data is stored, adjust age rules, add exceptions, collect emails or phone numbers, or even delete records. So, what started simple is now a headache. Even if these changes sound small in its own, but together they add up. And unless the system was built with flexibility in mind, even these basic updates can cause the whole program to break. That's how something simple starts to get complicated very quickly. And this is exactly what happens. The app that once worked perfectly fine suddenly starts failing everywhere. One small change creates a ripple effect, and instead of improving, everything starts collapsing. Whether you're building a simple calculator or the next big app, even the smallest programs need solid foundations. So, first, your code needs clear logic. Every function should have a single obvious purpose that anyone can understand at a glance. Second, establish well defined rules from the start. Consistent naming conventions, clear data structures, and predictable behavior patterns. And make your code easy to modify because trust me, guys, you'll be changing it. Modular design and loose coupling are your best friends. And finally, build defensively. Handle edge cases, validate inputs, and plan for things to go wrong because they will. Small mistakes shouldn't bring down your entire program. Now, these principles aren't just theoretical, they're the foundation of how professional software gets built. So now meet SDLC or Software Development Lifecycle. This isn't just a fancy acronym, it's the roadmap every successful project follows. Whether you're working solo or with a team of hundreds, the SDLC gives structure to chaos. Planning, developing, testing, and deploying. Each phase builds on those core principles we just discussed. We'll go more in depth later on. It's how ideas become reality and how small programs grow into systems that change the world. But how does this actually look like in practice? It's simpler than you will think. First, understand what to build, talk to users, research the problem, define clear requirements, and then design it properly. Sketch wireframes, plan your architecture, think before you code, build it step by step with those solid principles we discussed. Test everything, because if you don't find the bugs, your users will. And then release it to the world. But remember, you're not done yet. Keep improving it based on feedback, fix issues, add features. The cycle never really ends, and that's the beauty of it. What exactly is a process? Think of it like a recipe. It's your step by step plan to complete a task or build something. In software development, a process means all the stages needed to create and maintain software. Just like baking a cake, you need the right ingredients, the right order, and the right timing to get something that actually works. Here are the core phases every project goes through that we mentioned earlier. Requirements, where you figure out exactly what needs to be built and why. Design, where you plan the architecture, user interface, and technical approach before writing a single line of code. And development, where you actually build the thing, turning designs and requirements into working software. These three phases are your foundation, but they're just the beginning. But here's the thing, having a great process framework like SDLC isn't enough on its own. You have to have the perfect roadmap. But if your code is messy, unreadable, and fragile, your beautiful process falls apart. So structure means nothing if the code inside it is a mess. You can follow every SDLC phase perfectly, but if your functions are tangled, your variables are confusing, and your logic is scattered everywhere, you're building a house of cards. Clean code isn't optional, it's what makes everything else possible. So this is Amir, and not like if this code, when you write an unclean code and then you check it later on, you'll not even realize it's your own thoughts. So what is a clean code? A clean code is readable. It makes sense when you come back to it months later. It's modular, split into small focused parts that do one thing well. It's well named. No more mysterious variables like x or temp2 or functions called I don't know fix. It's self-documented through clear names and helpful comments, and it's robust. It doesn't crash when something unexpected happens. Clean code is code that respects the person who has to read it next, even if that person is you. But here's the catch. My clean code isn't clean for you, and your clean code isn't clean for me. Clean code is subjective, and that creates a problem when teams need to work together. So that's why design patterns exist. Design patterns are reusable solutions to common problems encountered during software development. They are not concrete implementations, but rather templates or blueprints for how to structure code to address specific design challenges. Teams need common solutions to recurring problems. Everyone was reinventing the wheel differently, and projects became too big for just writing clean code alone. Design patterns help maintain consistency, scalability, and clarity across entire teams and projects. They're easy to maintain because changes happen in one time. They're usable templates that save time, and they're simple to extend when requirements change. Think of them as the shared vocabulary that lets the developers communicate complex ideas quickly and clearly. Design patterns can be creational, procedural, and functional. We're not gonna get in details for the types, but you can read about them in the website that I'm gonna show you later. Example of design patterns are singleton, adapter, mediator, factory, pattern matching, and function composition. But that's also not enough. While design patterns help solve specific coding problems or structure features, design principles provide the fundamental guidelines that shape both code quality and system architecture. Patterns are the what specific solutions you can apply. Principles are the why, the underlying philosophy that guides all your design decisions. So you need both design patterns and design principles. But principles always come first. This is a website for those interested in digging deeper. You can check the website, and it has the source gives a thorough explanation of design patterns, their background, purposes, and categories. Design principles aren't just rules written in a handbook somewhere. They're the invisible framework that shapes how we think about code before we even open our IDE. Think of them as your coding compass. They point you in the right direction when you're lost in a sea of possibilities. These principles guide our mindset, helping us make better decisions about structure, readability, and maintainability. They're the difference between code that works and code that thrives. Um, these are some design principles. Yagni, the art of not overdoing it. It teaches us the power of restraint. It's the human nature to want to build for every possible future scenario. But Yagni reminds us that prediction is hard, especially about the future. When you're tempted to add that extra feature just in case, Yagni whispers, do you actually need this right now? This principle saves us from bloated code bases, over engineered solutions, and the maintenance nightmare that comes with unused complexity. Yes, as keep it simple and stupid. Simplicity as a superpower. This isn't just about dumping down your code, it's about smart simplicity. The best solutions often look obvious in hindsight, but they require real skill to achieve. Simple code is easier to debug, easier to test, and easier for your future self to understand. So when you're solving a problem, ask yourself what's the simplest thing that could possibly work, then build that. And complexity will find you soon enough without you inviting it in. And dry is the third principle we're gonna talk about. It's don't repeat yourself. It's about more than just avoiding duplicate code. It's about creating a single source of truth. And every single piece of knowledge in your system should have one authoritative representation. When you violate dry, you're not just creating more lines of code. You're creating multiple places where bugs can hide and inconsistencies can creep in. So that's why remember, dry applies to logic and business tools, not just code. Sometimes similar looking code serves different purposes. And we're gonna now talk about system architectures. Examples of system architectures are monolithic architecture, microservices architecture, event source architecture, hexagonal architecture, and actor model architecture. A monolith is one big application. Everything runs together, uses the same database, and is deployed at once. It's simple and good for small projects. While microservices architecture split the app into small parts, each part does one job, has its own data, and can be deployed alone. It's good for big teams, but harder to manage, definitely. Event driven architecture in this style, parts don't talk to each other directly. They send out events and others listen and react. This makes the system flexible and able to handle a lot of work. Hexagonal architecture, or ports and adapters, keeps business logic in the center. Things like databases and APIs connect from the outside. This way, the core logic stays clean. Now, finally, actor model architecture. In the actor model, everything is an actor. Each actor has its own state and talks to others by sending messages. It's great for systems like chats and games. This is a table that you can refer to later. It goes deeper into design patterns, principles, and system architecture. Now, many people think software development ends when you finish coding, but that's just the beginning. The software development lifecycle has six crucial phases: requirements gathering to understand what needs to be built, design to plan the solutions, development where you write the actual code, and testing to find and fix bugs, deployment to release to users, and finally maintenance to keep it running and evolving. Each phase is equally important. Skipping testing leads to buggy software. Poor deployment causes downtime, and without maintenance, even great software becomes obsolete. So, development is just one piece of the puzzle. DevOps combines development and operations into a unified approach. It's about breaking down the traditional wall between developers who build software and operations team who run it. So instead of developers throwing code over the wall and hoping it works in productions, DevOps creates collaboration throughout the entire software's lifecycle. This means faster releases, fewer bugs in production, and software that actually meets business needs. So, in short, SDLC defines the process. It's the roadmap that shows what steps to follow when building software. DevOps powers the execution. It's the engine that makes those steps happen efficiently and reliably. Think of SDLC as your recipe and DevOps as your kitchen equipment and cooking techniques. You need both. The recipe tells you what to do, but without good tools and methods, even the best recipe won't turn out well. DevOps is a set of practices that automate and connect software development on IT operations, covering everything from building code to monitoring production systems. It includes continuous integration to catch bugs early, automated deployment to reduce human error, and infrastructure as code to manage servers consistently, and comprehensive monitoring to spot issues before users do. So the goal is delivering a software reliably and quickly while meeting business needs through seamless collaboration between development and operation teams. And now let's get into coding.